This is AQA A-level Chemistry. It is a required practical question based on RPA2. So I'm going to let you have a go, pause it on each section, try it on paper, and then review. So to begin with, if you pause on parts A and B, and then we have parts C and D. So let's go through and review the answers. Question is about enthalpy changes. What is the meaning of the term enthalpy change as applied to a chemical reaction? Well, we know that enthalpy is delta H. We know it's related to energy, but why is it enthalpy, not energy? It's because it is taking place at a constant pressure. So that's the additional information that you need. For part B, this is a 6 marker. Now on 6 markers, there are clear marking criteria to determine what level you are going to be working within. I'll talk more about that later. But first of all, let's bear in mind with the question, we are looking at reading the method, making improvements. I'm going to go through the indicative chemistry content. And of the 3 stages, which there are always 3 stages in these questions. The first stage is related to apparatus. How could we improve in terms of apparatus? And what we're looking for here is we can see that we are using a measuring cylinder to measure the volume. Well, a clear improvement is to use a burette or a pipette instead. You could also use a polystyrene cup instead of a glass beaker. That's going to be a much better insulator. It's going to minimize heat loss. And talking about re-weighing the watch glass after adding the solid. That way we're weighing by difference. We know the exact amount that has been added. And also could talk about using a powdered solid rather than 2.5 grams of solid calcium carbonate. That would mean the reaction would take place more quickly. It would certainly be more effective in terms of generating heat energy before that heat energy gets lost too rapidly. The second stage in this experiment is to look at temperature measurements. And one of the recommendations here is to record the initial temperature for a few minutes before reacting. Now, there is a graph that you will be familiar with where you extrapolate a line before the reaction begins and extrapolate a line after the experiment begins. And they both go to the same point in time. That's how we get our theoretical maximum temperature rise. So that's not happened here. We could do. And measure at regular intervals afterwards until a trend is observed. So that fits in with that same idea of the graph. Finally, temperature determination. You could then plot a graph of temperature versus time. You could extrapolate to the point of addition. And then determine delta T at the point of addition. So we've got our 3 stages there really clearly. And to get 6 marks, to get level 3, all stages need to be covered and virtually complete. As a rough rule of thumb, you're going to want the majority of what's in this section. So 2 or 3 out of the 4, 2 out of the 3, probably both of them here. That would count as virtually complete. And if all 3 of them are virtually complete, you're into level 3. If 2 of them are virtually complete, or there is something from all 3 of them, it's level 2. If 1 is virtually complete, or there is something from at least 2 of them, that puts you at level 1. So you can work through and see how many marks you think you would have got. So this table is really important, and it does stay fairly similar whatever the question is. It's always a similar criteria as we're marking. But I just want to highlight what it is that this question relates to, and I'm going to draw the graph that I was talking about earlier. So you can have temperature against time, you take the measurements, but we've not taken a measurement here at minute 4. Once we do that, at minute 4, we can see that's where we would like to see an instantaneous increase in temperature. I extrapolate forward with my initial temperatures. This is what would happen if the reaction had never taken place. I extrapolate backwards, and that allows me to see what the temperature would have come down from following that cooling curve. And that then allows me to work out delta T based on the graph readings. Okay, carrying on to parts C and D. So for part C, different experiment, we have got a concentration and volume of HCl, same for NaOH. Well, I'm going to start by calculating the number of moles of HCl. I could do it with HCl or NaOH because they are equal in amount. Neither of them are in excess. So I've got my concentration, 0.5 mole dm to the minus 3, and I've got my volume, which is 50 cm cubed, but I'm converting it to dm cubed by dividing by 1,000. That's so that we've got a consistency of units across these two. And it allows me to see that we've got 0.025 moles. From there, I want to calculate Q. Now Q is measured in kilojoules. The actual calculation comes out in joules, but we've got negative 57.1 kilojoules per mole. So from 0.025 moles, I would have actually generated 1.4275 kilojoules. So we're working out Q almost going backwards through the calculation there. But it is now important that we consider that Q is MC delta T. We are interested in the temperature, the final temperature that's reached. So let's rearrange that and make delta T the subject. It's Q over MC. Well, Q, I've just calculated, is 1.4275 kilojoules. However, in the Q is MC delta T calculation, it must be in joules. So I'm multiplying by 1,000. I'm then dividing by mass. Remember, this is the mass of surroundings. 50 centimetre cubed of HCl, 50 centimetre cubed of NaOH is 100 cm cubed in total. Assuming a density of 1, that means the mass of the surroundings is 100 grams. And I'm multiplying that by specific heat capacity that will always be given. That's 4.18. Once I've done all of that, I've got my delta T value. T has gone up by 3.4 degrees C. But look at the question carefully. It's not asking for the change in temperature, it's asking for the final temperature. So I need to take my 18.5 that I started with, and I'm adding 3.4. So my final answer for part C is that the temperature went up to 21.9 degrees C. On D, suggest how, without changing the apparatus, the experiment in part C could be improved to reduce the percentage uncertainty in the temperature change. If we're reducing percentage uncertainty, we are going to want increased concentrations of solutions. If we do this with concentrations that are higher, we're actually going to get a more vigorous reaction in the sense that more energy is going to be released. So there will be bigger temperature rises. The uncertainty on the thermometer hasn't changed. If it's plus minus 0.15, I'm now doing plus minus 0.15 degrees C on a much bigger temperature, which brings my percentage uncertainty down. That takes us to the end of this question. Thank you for listening, and goodbye.